So welcome everyone. This is another talk in the series from the Cambridge Institute of Astronomy. My name is Nina and I'm gonna be your speaker for today. For those of you who just joined, we have a few quizzes throughout the talk and these are performed using Slido. So if you want, you can download Slido on your smartphone and using the hashtag bang or the QR code that I have it here, you can interact with me and answer the questions and ask questions, which if I have time I will go through at the end of the talk. Okay, so let's start. So today what we're going to be talking about is the Big Bang and the beginning of the universe. So many of you might have heard already that the universe started with a Big Bang, but you might not know exactly how. So that's what we're going to go through today. So I think most of us, at least once in our lifetime, we go and we ask questions such as, where did we come from? And why are we here? And those are really philosophical questions. And they are hard to get an answer for. But astronomy can help us a long way into answering those questions. So for example, you could say we are living beings and we only are here because we have a nice planet like the Earth. So the Earth has an atmosphere that is thick enough to protect us from harmful radiation from the sun. The Earth is also the right temperature. It's not too hot so that we would all get burned, neither too cold so that we all would freeze. And at this temperature it's really nice because we can also get water in the liquid form. We can get liquid water, which is very important for life. So if you have a planet like the Earth, then you could say that given the right conditions, life like us could exist. But what do you need to create a planet? Well, to create a planet, what you need is a star. So this is a picture of a star that is forming, that we took with a telescope called ALMA. And the star that is forming is this yellow blob in the middle. And you can see that around this yellow blob you have a lot of other material in a disc shape. So this is what we call an accretion disk. And around this disk you can see that there are regions where there's red and orange. These are the bits of the disk that have gas and dust that we are seeing. But there are also some regions, some orbits, some circles around this star that is forming. They're completely black. And we think those places are where planets started to form. So the planets start forming there and they start gathering all the dust and all the gas that are in those orbits. And so those orbits suddenly are not emitting light anymore and we see them as dark circles. And astronomers got really excited when we took this picture because this is one of the first picture that showed planets forming. So that's how a planet comes to be. And if we were to look at this same region of space millions of years from now, what we might see is something really similar to our solar system. So you would have a star in the middle and a bunch of planets orbiting around that star. There wouldn't be any more gas and dust around as much because either that gas and dust would have accumulated onto a planet, or it would have formed a little rock, or it would have been completely blown away by the radiation of the sun. Okay, so if we have a star, we can potentially have a planet, and if we have a planet and it has nice conditions, we can potentially have life. But how do we create a star? How can we get to a star? So to get a star, you have to have a lot of material. The sun has a lot of mass. So you have to have a region of space where there's a lot of gas so that you can form a star. And you can only find those regions in what we call galaxies. So we know that we live in a galaxy called the Milky Way, right? And here is an illustration of it. Obviously we can't see the Milky Way because we live in it, so we would have to send a probe all the way into outer space, much further away, to take a picture like this. So we don't actually have a picture of the Milky Way, but this is how we think it looks like. So it has these spiral arms and really nice shape. And it has a lot of gas. So if you see the browny stuff there, those are all gas particles and dust particles that we are seeing. And this gas can, if it gets churned, it can form eventually stars. Okay, so if we have galaxies, we have stars. If we have stars, we can have planets. We can have planets. We can have life. But what creates those galaxies? And this is partially what we're gonna be talking about in this talk about the Big Bang and the beginning of the universe. So to start answering this question, we have to kind of go back in time 100 years, which is not too much. 100 years ago, astronomers were for the first time looking at galaxies that are not the Milky Way. Before then, we thought that the Milky Way was the whole universe. But then we realized that there were actually other galaxies out there, and the universe was much bigger than we thought. So, what the astronomers wanted to see how far away can I see a galaxy, because they wanted to see how big the universe was. So they started looking at galaxies that were really far away. And when they looked at galaxies that were far away, they got a bit surprised, because they all looked a bit red. And the further away the galaxy was, the redder it looked. And they were really confused by this, and they were trying to find an explanation. And I would like you to think about that as well. So this is our first quiz time. So if you who are watching who have Slido, we are gonna do the first quiz. So why do you think that the light from the galaxies, faraway galaxies, was redder? So you can vote now. So we got one vote already. I'm gonna wait until most of you can switch to Slido and vote a little bit. Okay, so if we look at the answer now, so the reason is because the universe is expanding. And you might say, well, how does red light tells us that the universe is expanding? That's what we're gonna see now. So the first thing you have to think about is that light is a wave. It's a wave sort of like the waves that you see in the sea, or if you do ripples on a swimming pool. But what is waving there is not space, is not a material, it's the electromagnetic field. That's what we call light, an electromagnetic wave. And different types of light have different types of wave. They wave in a different way. Some wave faster and some wave slower. So you can see that, for example, the light of the sun, we think that it's white, but if we use something called a prism, then we can make all the lights that are slightly different, that wave in a slightly different way, split up. So that's what we see here. And every single one of the colors of the rainbow there has a particular type of wave, a particular type of light. And their difference is what we call the wavelength. So what we see here is that the red light is very stretched, very long, and that's what we say it has a big wavelength. And the blue light is very short, it's kind of little chopped. And this is a short wavelength. And you could take every single color of light, and each one of those would have a different wavelength, right? So how does that get us to the universe expanding? Well, what you can think about is that if you could take a blue light and stretch it a little bit, then you would get green. And if you could stretch it even more, then it would get red. So what scientists realized is that an expanding universe could make light look redder. So if you think about the universe as being a balloon, right? So imagine this little tiny balloon here at the left hand side. And then I have two galaxies, one on one side of the balloon and one at the other side of the balloon. As the universe is expanding, the light that's being sent from one galaxy to another also expands. So where I had kind of purpley light can become blue light. And if I stretch that even more and the universe expands even more, then this light is going to go green. And if it goes even more stretched, then their light is going to go red. So galaxies that are very far away, their light looks red just because the light that they emitted got stretched as the universe expanded. So that's how we know that the universe is expanding. Now, what we can do now is we can play a bit of detective. So we know that the universe is expanding today, so that means that in the past, if I could go on a spaceship that travels in time, if I went to the past, the universe must have been a little smaller. And if I went even further into the past, it must have been even smaller, right? So, and now I want to ask you again, so how big do you think the universe was when it first started? So, if we go for our next question, so how do you think the universe was? Do you think it was small and very cold? Almost as big as it is today, but much hotter. Still big, but cold as there were no stars. Or very tiny and very hot. So if we look at the answer now, so the universe was very tiny and very, very hot. Okay, you are doing very well on these questions, by the way. Well done. So let's see why. Okay, so actually the whole universe, we think that at some point, at the very beginning, at the point where we call the Big Bang, was smaller than the size of an atom. And if you don't know what an atom is very small building blocks of everything that we see. So I'm made of atoms, you're made of atoms, the whole universe is made of atoms. And atoms are so tiny that there are more atoms in a grain of sand than grains of sand in all the beaches on the earth. So there are lots and lots of atoms around, and they are very, very small. But the universe at one point was even smaller. Now, imagine trying to compress everything we know, all the galaxies, all the stars, all the planets, all the gas, everything, into a very small space. When you do that, what happens is that it gets very, very, very hot. It's kind of similar, I don't know if you ever tried this, but when you pump a lot of air into your bike tire, then sometimes it heats up a bit. That's because you're compressing gas inside the tire of your bike. And it's the same thing, but now you're compressing a lot more material, so it gets even hotter. And at that point, the universe had 1 billion degrees Celsius. It was incredibly hot. It was so hot that nothing could stay around intact, not even atoms. So atoms are made of smaller things, and those smaller things were all broken apart because nothing could keep together. They were all whizzing around in a big soup, which we call the primordial soup. And this primordial soup was made of lots of different particles, and the most important ones are the ones that I put here today. So they were the electrons. So the electrons are these orange little balls with a minus sign, and they have a minus sign because they have a negative electromagnetic charge, electric charge. They have the little ducks here, which are my quarks, and the little tubes of glue, they are my gluons, and they're gonna be the most important things in the story I'm gonna tell you. And at this point, it was very hot that we call a quark gluon plasma. So it's similar to the plasma that it is in the sun, but it's slightly different components. But it was very, very hot. Now, as the universe, after the Big Bang, the universe was expanding. And as the universe expanded, it could start to cool down. And when the universe cooled down, at some point, it was cold enough so that it could create a few of the first particles that are made out of quarks and gluons. So gluons, they tend to kind of work as a glue that ties different quarks together. So here you can see two different particles that are made of quarks and gluons. One is the proton, so those are the ones in green, and they have a positive charge, so they're different from the electrons, they have a negative charge. And the other ones that are here in pink are the neutrons, and they have a neutral charge, hence the name neutrons. And all of that, from going from this hot soup to these other particles, it all happened in less than a second. But then it took a very, very long time until the picture of the universe changed a little bit. In fact, it took 300,000 years. And at that point, the universe started being able to form their first true atoms. So it formed atoms of two elements, hydrogen and helium, because those are very simple. At that point, the universe was only 3,000 degrees C. It's still very hot, but if you imagine that's colder than the sun is, so it's not all that amazingly, unimaginably hot anymore. Now, the universe only created these two because it didn't have enough energy in the collisions to form elements that were more complex than these ones. So as you can see, hydrogen is very simple. It has a proton in the middle and a little electron going around it. And the helium atom has two protons, two neutrons in its nucleus, and it has two electrons whizzing around it. Now, at that point, after the Big Bang, we created 75%, or 3/4 of the universe was hydrogen, and 25%, or 1/4 of the universe was helium. And amazingly, that's still very much like it is today. So if we were to take everything in the universe and see what it's made of, the universe is still, 3/4 of the universe is still hydrogen. 24% of the universe, it's still helium. And this hydrogen and helium is still mostly hydrogen and helium that were produced all the way back then, 13.8 billion years ago, when the Big Bang started. And 1% of everything that there is in the universe, everything that we can see, is everything else. So if you think about you have iron running in your blood, you have calcium in your bones, you have carbon, the atmosphere is full of nitrogen. All of those other elements, they were produced afterwards, after the Big Bang, later by stars, when they made new elements via what we call nuclear fusion. But that doesn't matter. What matters here is that the composition of the universe is still very similar to the one that the Big Bang created. And this is a very good clue that points us towards the Big Bang, because we can't explain why we have this amount of each element otherwise. Okay, so now I want to do the last quiz. So if you all go back to Slido, I want to ask you, why do you think this time where the atoms formed is important? Before the first atoms formed, what do you think the universe looked like? Do you think it looked like a thick fog? Do you think it looked transparent? Do you think it had no light? Or didn't have stars, only dust? So let's look at the answer. The answer is that the universe looked like a thick fog. Let's see why that is the case. So before atoms formed, the electrons, remember the electrons, these negative particles, they were scattered all around. And what happens is that because electrons have a negative electric charge, every time that an electromagnetic wave or light kind of goes near it, it has to interact. So light would travel a little bit and then interact with an electron. And then after this interaction, light would change its path a little bit and interact with and travel a little bit and interact with another electron, and so on. So the light would get a very ziggy-zaggy pattern through space. And it was very hard for light to travel without. So this is very similar to what happens when you have fog. So here it's a very thick fog in a road. So what's happening there is that light is interacting with all the water particles that you have in the air, and because of that you can't see very far away. So here the water particles are doing the same thing that the electrons were doing in the early universe. So the universe looked like a very big foggy place. It wasn't very nice. But when you got the first atoms forming, then you can see that the atoms are made of, for example, hydrogen is made of a proton and an electron. So the overall charge of the atom is neutral, because you have a positive plus a negative, it becomes neutral. The helium, the same thing. You have two positives, you have two green protons at the nucleus, and two orangey electrons in the outside, and that makes it also neutral. And at that point, light didn't care anymore if there were protons and electrons around. It could just travel freely through space. And at that point, the universe became transparent. And you can imagine how amazing it must have been to see a complete, opaque, foggy universe become all of a sudden transparent. And at that point, when it became transparent, was as if every single point in space turned on a light bulb. So there was a big flash of light in the universe. And you might say, well, why is this important? So to explain why this is important, I'm going to tell you a little story. So a few decades ago, two scientists, Arno Penzias and Robert Wilson, they were working in this antenna, which is called a horn antenna because it looks a bit like a horn. And in this antenna, they were trying to detect some waves, but they had a noise in their detections. And that noise was in the frequency of microwave light. So, you know your microwave oven? Yes, the microwave of your microwave oven is also a type of light. It's a type of light that has a different wavelength. Remember the wavelengths that we were discussing? So it's a type of light we cannot see, but antennas can. And they were detecting this microwave light, and they didn't know where it came from. And they pointed this antenna in every single direction they could, and they still had this noise. So it wasn't anything that was emitting it on the Earth. They even thought at some point that it was because birds were pooping in the antenna. So they had a problem that lots of birds would go and nest in the antenna and go to the toilet there, which wasn't very nice. But then even after they cleaned all the poop from the antenna and took the birds away, that noise remained. And then at one point they had this discussion with an astrophysicist, and they realized, oh my god, what we are detecting is that flash from the very early universe. And this flash from the early universe that we managed to detect is what we call the cosmic microwave background. So it's cosmic because it comes from the cosmos, from the universe. It's microwave because the light is of the microwave type. So the same ones in your microwave oven. And it's background because it covers everywhere. It's like the background of your screen. The background of your computer screen covers the whole screen. This microwave background covers the whole sky. It doesn't matter where you look in the universe, it's always there. And we got so excited about this that we decided to send a satellite to space to make more accurate measurements of this cosmic microwave background radiation. And this is what we got. So here on the right hand side we have the Planck satellite, and this big ellipse is a map of the sky if we measure the CMB at every single point. And here you can see that there are some regions that are red and some regions that are blue, and it seems that it's very different, but actually if you say that the blue region is 1, then the red region would be only 1 in 1,000th part different from the blue region. So if blue region were 1, the red region would be 1.000001. So the sky is actually pretty uniform in this cosmic microwave background. And that's how we know that it came from the early universe. Because if you look at the universe now, it's pretty complex. It looks pretty different depending on the direction you look. If you look in one direction, you might see a galaxy. If you look in another direction, you might not. But the universe early on, just after the Big Bang, 300,000 years after the Big Bang, was incredibly uniform. And that's why we can see this very uniform radiation coming from the whole sky. Right? Now, these minute differences, though, are very important, because those differences were what created everything else that we see today. Why? Well, because in the early universe, when you had a little bit of space that had slightly more mass, then because of gravity, that place that had slightly more mass could attract more mass towards itself. That's how gravity works, right? If you are massive, you can attract mass. That's the same way that the Earth, which is very massive, pulls us. We have a little bit mass towards the center. That's why we don't go floating off in space. And that's the same thing there. So you had a little bit of mass, it attracted mass from gravity, so it got more massive, and then it had even more gravity. So it could attract even more mass, and this was sort of a runaway effect. And it is this way that you could accumulate enough mass in one region of space to form galaxies, while other regions went almost completely empty, like the space in between galaxies. And of course we can't see any of this, but we can simulate, we can use a computer to do simulations on how the universe looked back then. And that's what I'm going to show you now. So what you are going to see now is that the universe was uniform, and then it starts accumulating from gravity in certain points. And what it forms in the end is this thing that looks a lot like a net or web. This is what we call the cosmic web. And you can see the video is going here on a loop, and you can see this really nice web, and each one of those points of light would be a different galaxy, or maybe a cluster, a bunch of galaxies held together. So I want to show you one more video where this web had already formed, and that is evolving until today. So this is another simulation that astronomers have done. And what you can see this purple sort of filaments where gas and dust is moving towards this kind of hubs, and it is in these hubs that you form most of the galaxies. So there you have a lot of gas that's being compressed by gravity, forming hundreds of millions of stars all the time. And you also get stars dying, and when the stars die, they can have like supernova explosions, which you can sometimes see in the simulation. But that's basically how we think that the universe looks today. You still have this kind of a web that formed all the way because of these really tiny differences on the early universe. So I guess this is the end of the talk, or the end of the beginning of the universe. So now I'm gonna go back to Slido and I'm gonna answer a few of your questions, okay? Thank you very much for watching. So if we go to the Q&A, okay. So Malachi asked, was there anything before the Big Bang? A little bang, perhaps. The answer to that, we're not really sure what banged the Big Bang, if you know what I mean. In a way, the Big Bang is the place where space and time started. So you might have heard that space and time are not completely separate. They are kind of two sides of one coin. They are together in something that's called space-time, right? So when the Big Bang came about, it created space and time for the first time. So it's kind of impossible to ask what was before the Big Bang. But yes, we try to think of something that could trigger a Big Bang. And some people talk about theories like the M theory, which is the membrane theory, which you have huge membranes, and when one membrane touches another, it creates a Big Bang. But the answer to that is we don't really know. So I hope that sort of answered your question. Okay. So what was before the Big Bang? That is sort of the same. So can the Big Bang happen again? So some people say, so there are different ways that we can think about the evolution of the universe. So one of the theories that existed at one point is one theory that was called the Big Crunch. So that was that the universe was expanding, and then at one time it would stop expanding and contract again and bang again, and it would do this kind of cycle forever. However, observations that we have from the galaxies actually show that they are not only that the universe is not only expanding, but this expansion is accelerating. We don't know what is causing this expansion to accelerate. It's something that we call dark energy, but we don't really know what dark energy is. But it causes this accelerated expansion of the universe. So in a way, the Big Bang is not gonna happen, at least we think, again for this universe. But if we could figure out what causes a Big Bang in the first place, maybe there was a Big Bang that created, for example, another universe that's not ours. We don't know. Okay, so Miles asked, what amount of space did the Big Bang affect? So space, as I was saying, didn't exist before the Big Bang. So you could say the Big Bang affected the whole of space because it created the whole of space. It's kind of hard to get your head wrapped around it, but there is no outside of the Big Bang, if you know what I mean. So as the Big Bang expanded, as the universe expanded, it was creating more space as it did so. So yes, the Big Bang created all space and therefore affected all space. So the Big Bang was very powerful. Actually, just after the Big Bang, the universe expanded very, very, very quickly. In a few seconds, it expanded from being smaller than an atom to the size of a galaxy, and then it continued expanding. And yes, in a way, it did produce light because the universe was very hot. And in a way, everything that is hot emits light. So, for example, if you have a toaster at home, you know, when you turn the toaster on, the little metal strips inside the toaster start glowing. They start glowing because they are hot. So the universe at that time was the same thing. The universe was very, very hot, so it also glowed, just like your toaster. And it did emit a lot of light, and it was very powerful because it produced everything. Okay, so thank Emma for the question. So Alexander and Tristan asked, who first came up... okay, it kind of went down, but I'm gonna answer that with the name Big Bang. Actually, that's a bit of a funny thing, because the Big Bang was a name that scientists used to mock people that believe in the Big Bang theory, because we didn't have proof for it. We still don't have proof, but we have a lot of evidence that shows that it's likely to be true, such as like this cosmic microwave background and the elements in the universe, as I talked in the talk. But they were kind of mocking scientists that believed in this type of theory. It's like, it's like a big bang, and they were making fun. But once it became the accepted theory, people actually started using the mocking name for the theory itself. I don't think everybody was incredibly happy about it, but it stuck, and it kind of has a nice, sound to it. How many Earths can you fit inside of the biggest star? That's a hard question, but you can fit at least a few 100,000. So the sun actually is a pretty small star compared to the biggest stars that we find in the universe. There are stars that are much bigger than the sun that fit tens, almost 100 suns inside them. And we believe that in the early universe, stars might have been even bigger. So the very first stars that formed out of the hydrogen and the helium of the universe, they were probably a lot bigger than the biggest stars that we see today. So yes, you can fit, hundreds of thousands of Earths on that. So despite having a solid core, how does Mercury have a magnetic field? To be honest, I'm not particularly sure about the answer to this question, but I guess we don't really know how the magnetic field is created. We know that it has to do something about having an iron core and it churning, but the fact that if you have anywhere in the planet where you have sort of a magma that's moving around, in theory that would be enough to create a magnetic field. But for example, the Earth magnetic field switches polarization every hundreds of thousands of years, and we actually can see that in rocks. That the North Pole magnetic pole becomes the South Pole, and the South Pole becomes the North, and we don't really understand how this changes or how it is formated, but it's something that we are trying to understand. So thanks, Prajit, for the question. So doesn't the accretion of planetesimals violate the second law of thermodynamics? So the second law of thermodynamics, so the answer is no. And the idea of the second law of thermodynamics is that everything becomes more chaotic with time in a way. So what you can think of, the second law of thermodynamics is that it says that it is going to turn out in the way that, most things are differently distributed in a way. So no, by forming planets and forming stars and forming galaxies in different areas, then you're actually making everything more diverse. So you're agreeing with the second law of thermodynamics instead of disagreeing with it. Okay. So if we could travel faster than the speed of the universe expanding and travel beyond the edge of the universe, what we would find. So that's from James, and thanks, that's a very interesting question. So that's the thing, there is no edge of the universe. You can think of the universe as being that surface of the balloon that I was talking about, right? So if you imagine, you can travel on the balloon forever around the balloon, and you'd never find an edge. So I think the universe is like this. So there is no space outside the universe, because as the universe is expanding, it's creating space itself. So in that way, yes, you can't do that. You can't really travel to the edge of the universe. Otherwise, you could think that there is a galaxy or a star that's hanging exactly at the edge of the universe, and that's not the case. All the stars and the galaxies, they are distributed into this expanding space, but there is no edge to it. So I already kind of answered that question, so I'm gonna jump. So the quick answer for somebody who just turned on is we don't really know. We only have theories. So that's a very interesting question from Alice. What color would you have if you stretched red light? So if you stretch red light, you don't get a color because our eye can only see a few colors. So you can see all the colors in the rainbow, but if you stretch red light even more, what you get is what we call infrared light. And this infrared light, like the microwave light I was talking about, is invisible to human eyes. You would have to put infrared goggles, so like special type of glasses, to be able to see that light. So we can create robots and telescopes that can see that type of light, but us with our normal human eyes, we can't. But that's what you would get. You would get infrared light. Did aliens form from the Big Bang? So this is from Seb. Seb, we do not know. We don't know any other place in the universe that has life like we have here on Earth. But we also know that the universe is very, very big, and that we have billions and billions of stars. So each galaxy, like our Milky Way, has billions of stars, and we think there are billions, if not trillions, of galaxies out there. So if you imagine that even a fraction of those have planets, and even a fraction of those planets are like the Earth, there could be other places that have aliens. There probably are, but we haven't seen any of them. Now, it also depends on what you mean by aliens. So it's very likely that we have some other type of life, similar to like a bacteria or a virus, that we might find someday in outer space. But then intelligent life would take also, millions of years of evolution for you to create something that was maybe intelligent like us human beings. So hopefully we are gonna find life outside in the universe at some point in the future. So who were the first people to study the Big Bang, and when did they? So the theory of Big Bang was highly advocated by a guy called Edwin Hubble, and this was in the 1920s was when they started coming with theories like that. So about 100 years ago. But we got better and better evidence for this as time went along. And for example, the Planck satellite that I showed the picture there, that's from already 2000, so not that long ago, that we're still building information about what happened and how it happened. Okay, thank you, Alice. So I'm gonna last one from George. Will our galaxy Milky Way ever merge together with another one? That's a very good question, and the answer is yes. So although most galaxies are moving far away, like the overwhelming majority of galaxies are moving further away from the Milky Way also has a few sort of satellite galaxies. There are a few galaxies that we call the local group, and we are kind of bound together because of gravity, because they were close enough together that gravity didn't let the other one kind of go away completely. And we are gonna sort of crash into another galaxy called Andromeda, but that's gonna be millions of years from now, so you don't have to worry about it. Also, when galaxies kind of collide, there's so much space usually between the stars that even though they kind of join together, most of the stars never get to crash into one another. So they really just kind of get together and become one larger galaxy. Okay, people, so that's it for today. I thank you very much for watching, and I hope you come back to watch the rest of the series. Okay, thank you so much.